Hey everybody, so in this video I'm going to talk about the last section of the final, which is about the reactivity of atoms. We did a demonstration in class, right, where in some classes I broke a beaker using sodium, but the lithium was not as reactive. So sodium, it has greater reactivity than lithium. And if you look at your periodic table, sodium is actually below lithium on the periodic table, so it indicates that as you go down on the periodic table, right, the atoms become more reactive. And as you go to the left on the periodic table, the atoms become more reactive. So that's the first pattern that we've seen, that atom reactivity is higher to the left on the periodic table and lower on the periodic table. So we're trying to bring in some other data to help us understand what's the reason for these patterns, and eventually we're trying to understand the nature behind valence electrons and where you get them. So here, it states it here. The purpose of this data analysis was to show patterns of reactivity and how they relate to position on the periodic table, and state the meaning of valence electrons and where those numbers come from. So the first thing we looked at is this graph about Coulomb's law. If you got to read this part up here, it says Coulomb's law states that the magnitude of the electrostatic force of attraction or repulsion between two charges, that's the Q1 and the Q2, is directly proportional to the magnitudes of those charges, right? More charge means more attraction or more repulsion, depending on if they're both positives or both negatives, right? If you have a plus and a minus, they're going to attract each other. If you have two pluses and two minuses, they're going to attract each other more. And inversely proportional to the square of the distance. So what that's saying is the closer it gets, the more attracted it's going to be. So that's what this graph is saying right here, that you increase the distance between the electrons in the nucleus, and the force actually, the force of attraction is less. So again, these images here on the right also show that in a large atom, shown here on the right, when the distance is large, the attraction between the protons in the nucleus and the electrons on the outside of the atom are less attracted. But if in a smaller atom, if the protons and electrons are close to each other, the attraction is greater. So here there's a stronger force of attraction, and here there's a weaker force of attraction. The next graph we looked at was the atomic radius. Again, another way to say radius, right, is size. So something that has a large radius, like the sun, has a large size. Something that, like a marble, has a small radius, so it's smaller in size. And you can see here that as you go to the left on the periodic table, and as you go down on the periodic table, right, the atoms actually get larger, with CS on this abbreviated periodic table being the largest atom. And this actually is similar to the reactivity pattern, right, that we saw in that really initial demonstration we did with sodium and lithium and the properties of elements lab. We did reactivities with hydrochloric acid and copper 2 chloride. The next graph that we saw was about ionization energy. And remember, ionization energy is the energy needed to remove an electron. You can see that the noble gases, those atoms in group 8 on the periodic table, don't want their electrons removed. You need to add a huge amount of energy, right? Huge amount of energy to remove the electrons. Remember, if you're trying to separate something from something it's attracted to, and it's really attracted, it takes a lot of energy. But look at the atoms here in red. Those are group 1. It only takes a little bit of energy to remove those electrons. So if the attraction is weak, it doesn't take much energy to pull something apart, right, that's attracted to something else. So we're starting to get this picture. Large atoms like the one here on the right, when their attractions are weaker, it's easy to pull off this electron right here. In the image on the left, when the attraction is strong, it's really much harder to pull that electron off. In the next graph, we looked at electron affinity. Remember that affinity means attraction, or it means liking of something. So right there are certain atoms that want more electrons. And you see here, in this graph, the values are negative. What that means is that when these atoms get electrons, they actually release energy. And that's a positive thing, right? That's the thing that they want to do. They want to release energy. That's favorable. And you see the atoms that want the electrons the most are F, Cl, Br, I, At, these atoms in group 7. They only need one more electron and they become like the noble gases. And look at the ones down here that you actually have to put energy in to put an electron into the atom. These ones are the noble gases, and they are these metals way on the left side of the periodic table. So you're starting to see this pattern. The ones on the left side of the periodic table want to lose their electrons, and the ones on the right side of the periodic table, not the noble gases, but the ones right next to them, the nonmetals, want to gain the electrons. So we see these patterns of ionization energy in these ionization energy graphs, and you see there's patterns. These ones up here, these two, require a lot of energy to be removed from the atom. So what kind of electrons require a lot of energy to be removed? Those are the ones that are really close to the nucleus. So if we draw this, we can see that there's 2 dots in each one of these, right next to the nucleus, in that first orbit. And then you can see there's a pattern, right? There's an 8 here, an 8 here. We don't have 8 more in this carbon one, but we only have 4 more. So you can see 1, 2, 3, and 4. In potassium, there are 8 more, so 1, 2, 3, 4, 5, 6, 7, 8. And then in aluminum, there's 8 more. 1, 2, 3, 4, 5, 6, 7, 8. In aluminum, there are 3 more in the next energy level. So it's 1, 2, 3. And in potassium, there are 8 more, right? These 8 right here. 1, 2, 3, 4, 5, 6, 7, 8. And potassium, sorry for my mess here, has 1 more electron. That's much easier to remove. And that's on the outside. So I'm going to point to the ones on the outside so you can easily see them. Or at least more easily see them. And carbon has these 4. 1, 2, 3, 4. Let me get a different color here. So you can see these ones on the outside. These are called the valence electrons. These are the ones on the outside of the atom. These are the ones that are involved in bonding. That's the key here, is that these valence electrons are involved in bonding so they can be traded with other atoms. They can either be shared or they can be donated. And we'll talk about that second semester. You can see that carbon has 4 valence electrons. You can see potassium has 1 and aluminum has 3. And that was the quiz that you took yesterday or today, 8th period, in class. And you can write this. It actually tells you on your periodic table which atoms have how many valence. It tells you which atoms have a certain amount of valence electrons. It actually tells you on the top. It's in group 1A, it has 1 valence electron. In group 2, it has 2. We're going to ignore all the transition elements because they follow a different pattern. Group 3A is 3, Group 4A is 4, Group 5A is 5, Group 6A is 6, Group 7A is 7, and Group 8, the noble gases have 8 valence electrons, except for helium, which has 2. So in this last section on the handout, it asks you to write a sentence which combines the idea of atom size, force of attraction, and why some atoms lose or gain electrons. So let's think about these 2 examples. We have these large atoms and we have very small atoms. In large atoms, the attraction between the nucleus and the electrons that are on the outside is weak. So there's a weak attraction. Why? Because the distance is large. The distance is large. And when that is the case, that electron can be removed easily. And when it's removed easily, right, that electron it would rather lose its electrons than gain them. In the smaller atom, this attraction between the positive nucleus and the electrons is very strong, so it's a strong attraction between the protons and the electrons in the small atom. Why? Because the distance is small, as in Coulomb's law, and it's hard to remove them. Well, in a small atom, instead of removing them, they're actually going to accept electrons from other atoms because they have this extra space, right? They're not noble gases, and because the nucleus is really close to the outside of the atom, they can pull in the other electrons. So I hope this is helpful for the last section of the final. Good luck, and I'll see you in class.